U.S. Navy Arleigh Burke-class destroyer is one of the most powerful surface combatants ever built. Its Mark 41 vertical launch system holds 96 cells. Each one is capable of carrying a Tomahawk cruise missile, a standard missile air defense interceptor, or an anti-submarine warfare weapon. 96 cells, 96 potential strikes against any target within range. The ship can engage threats simultaneously across multiple domains, air, surface, and subsurface, while maintaining its position in a strike group formation and continuing to steam at combat speed. By any reasonable measure, it is a warship of extraordinary capability. But the moment it fires its last missile, it becomes tactically useless. It has to leave the fight. It has to steam to a port facility days away from its combat station, sit alongside a pier, and spend 3 weeks being reloaded one missile at a time by a crane crew working from a fixed surface. 3 weeks gone from the fight, because there is no way to put a single missile back into a vertical launch cell while the ship is at sea. This is not a theoretical vulnerability. It is an active operational constraint. And really, the disturbing part is that it shaped the entire conduct of Operation Epic Fury, the largest sustained naval missile campaign in the modern era. Over 5 weeks, 850 Tomahawk cruise missiles were expended against Iranian military targets. That number represents the most intensive use of the Tomahawk system in the weapon's operational history. Every destroyer and cruiser that fired its magazine dry had to make the same journey away from the fight to a port, 3 weeks off the line. The Navy's most capable surface combatants were cycling in and out of the combat zone, driven not by crew fatigue or battle damage, but by an empty magazine and no way to fill it at sea. The Mark 41 vertical launch system was designed for maximum firepower in minimum deck space. Its cells are arranged in modules, 8 cells per module. Each cell is a steel tube sunk vertically into the ship's hull, with the missile stored nose down inside it. When a missile is fired, the cell cover opens, the rocket motor ignites, and the weapon exits the tube in under 2 seconds. The system works with extraordinary reliability in this direction, out of the ship. The problem is the reverse. Getting a missile back into a cell requires lifting a 3.5-ton object from a loading position, orienting it precisely over a cell opening that is approximately 21 inch in diameter, and lowering it straight down into the tube without contacting the cell walls on a fixed surface with no movement. This is a complex industrial operation. It requires a crane, a trained crew, and careful alignment procedures. It takes approximately 45 minutes per missile under ideal conditions at a pier facility. At sea, none of those conditions exist. A naval vessel in open water is never stationary. It moves in 6 degrees of freedom simultaneously, rolling side to side, pitching bow to stern, heaving up and down, and combining all 3 motions in patterns driven by wave action, wind, and its own propulsion system. A destroyer in moderate sea state, Beaufort scale 4 or 5, which is routine operating weather, is rolling 3 to 5 degrees continuously and pitching 1 to 2 degrees. Those numbers sound small, but really, when they are applied to a 3.5-ton object suspended from a crane at the end of a cable, they become catastrophic. A pendulum effect develops. Immediately the moment the missile is lifted off its support, the ship rolls 2 degrees to port. The crane swings with the ship. The missile, suspended freely, continues moving in the direction it was already going because of inertia. The result is an uncontrolled swing of a 3.5-ton explosive device directly over an open vertical launch cell containing other loaded missiles. That is the real problem. And the Navy understood it when it designed the Mark 41 system. The decision was made deliberately. The system would be optimized for firing rate and magazine depth, accepting that reloading would require a port facility. That decision made operational sense in the 1980s threat environment. A surface action group expending its full magazine in a single engagement was not the expected scenario. Engagements were expected to be intensive, yes, but brief. The sustained campaign scenario, 850 missiles across 5 weeks against a continuously regenerating target set, was not the design case. So what had been an acceptable constraint in the expected scenario became the critical vulnerability in the actual one. And that is where the real lesson begins. 5 weeks, 850 Tomahawk cruise missiles. Those numbers do not fit comfortably into any previous operational planning framework for naval missile expenditure. The Tomahawk has been fired in combat in every major U.S. military operation since 1991, In Operation Desert Storm, approximately 290 Tomahawks were fired across the entire conflict. In Operation Iraqi Freedom in 2003, approximately 800 were fired across the entire campaign. Operation Epic Fury expended 850 in 5 weeks. That means it matched the entire Iraqi freedom total in 1/3 the time, against a target set that continued to regenerate as Iranian forces relocated, dispersed, and reconstituted their damaged infrastructure. The rate of expenditure was not the result of poor targeting or wasteful employment. It was the result of a target set that required continuous re-engagement as the Iranians adapted their tactics. And really, that is what made this campaign so punishing. The weapons worked, the ships worked, but the assumptions behind sustained use did not. The rotation cycle was operationally damaging, beyond the simple absence of a ship from the line. When a destroyer leaves its station to reload, its position in the strike group's defensive architecture has to be covered by the remaining ships. Anti-air warfare coverage begins to develop gaps. The anti-submarine screen becomes thinner. The ships that stay behind are forced to increase their own operational tempo to compensate, and that accelerates their own magazine expenditure. The problem compounds itself. The more missiles are fired, the faster ships cycle out. The faster ships cycle out, the thinner the remaining coverage becomes. By week 4, the strike group commander was managing a ship rotation that consumed as much planning bandwidth as the strikes themselves. And that was only the operational side. The supply side of the equation made the problem even worse. The Tomahawk cruise missile is not a mass-produced commodity weapon. It is a precision-guided system with a unit cost exceeding $2 million, manufactured in a production facility in Tucson, Arizona that has an annual production capacity of approximately 60 to 90 missiles per year in its current configuration. 850 missiles expended in 5 weeks, 60 to 90 produced per year. The arithmetic is straightforward, and the conclusion is deeply uncomfortable. At the expenditure rate of Operation Epic Fury, the Navy consumed more than a decade's worth of current production capacity in 5 weeks. The stockpiles that had been built up over years of steady-state production were drawn down in one campaign. Replacing them at current production rates will take years. The Navy has known about the at-sea reload problem for decades. It has not been ignored. The challenge of reloading a vertical launch system cell at sea has been the subject of engineering studies, prototype development programs, and operational testing efforts going back to the 1990s. The fundamental obstacle has always been the same: the pendulum effect of a suspended heavy load on a moving ship. Every proposed solution has had to address that physics problem before it could address anything else. The most recent attempt is the Transferable Reload at Sea method, or TRAM. Its approach to the pendulum problem is mechanical rather than electronic. Instead of trying to sense and compensate for ship motion in real time, TRAM eliminates the free suspension of the missile entirely. The TRAM system uses a fixed guide rail structure that constrains the missile along its entire length during the loading operation. The missile is not suspended freely from a crane cable. It is captured inside a rigid channel that runs from the loading position on the supply vessel directly to the vertical launch system cell opening on the receiving ship. The ship can roll, the ship can pitch, but the missile moves with the rail structure, which is mechanically connected to both vessels and compensates for relative motion between them through a controlled articulating joint. The pendulum effect is eliminated because the missile is never freely suspended. It is constrained at every point of its travel, from the supply position to the cell. That is what makes TRAM so important. The loading operation that takes 45 minutes at a pier can, in testing, be completed at sea in under 2 hours per missile, including the time required to establish the connection between the supply vessel and the receiving ship. But the truth is, TRAM is not operational. It has completed developmental testing and demonstrated at-sea reload capability in controlled trials. The engineering problems that made at-sea reload impossible for 60 years have been solved under controlled conditions with dedicated test crews and purpose-built equipment. What it has not completed is the operational testing cycle that would certify it for fleet use during actual combat operations. That certification requires training programs, qualified instructors, modified supply vessels, and new operational doctrine. None of that exists yet. So the TRAM system exists as a validated engineering solution to a problem that cost the Navy 850 missiles and 3 weeks of combat effectiveness per ship in Operation Epic Fury. It arrived one campaign too late, and really, That is where the frustration becomes impossible to ignore. The engineering answer to the reload problem is sitting there, tested, validated, and still waiting. Meanwhile, the fleet continues to fight under a logistics model built around a different era, an era when a warship was not expected to burn through its magazine in a sustained, high-intensity campaign against a target set that kept coming back. The result was a rotation cycle that did not just pull ships away from the battle. It steadily hollowed out the strike group from within, one empty magazine at a time. The production problem has no equivalent engineering solution waiting in a testing facility. There is no tram for the manufacturing capacity gap. Increasing Tomahawk production from 60 to 90 missiles per year to a rate that could sustain a campaign like Operation Epic Fury requires capital investment in production facilities, supply chain development for the precision components that go into each missile, workforce expansion at the manufacturing level, and a procurement commitment from the Department of Defense that sustains the increased production rate across multiple budget cycles. None of those things happen quickly. The fastest realistic timeline for meaningfully increasing production capacity is measured in years. 3 to 5 years at minimum for a significant capacity increase, and longer for a true step change in production rate. The next campaign will begin with whatever stockpile remains after Operation Epic Fury. That stockpile is dramatically smaller than the one the campaign started with. The Mark 41 vertical launch system is not a flawed weapon system. It is an extraordinary achievement of naval engineering that has given U.S. surface combatants a firepower to displacement ratio unmatched by any navy in the world. The Tomahawk cruise missile is not an inadequate weapon. Its accuracy, its range, and its reliability across Operation Epic Fury confirmed everything the system's designers intended. 850 missiles, 13,000 targets struck over 5 weeks. The weapons perform. The vulnerability that Operation Epic Fury exposed is not in the weapons. It is in the assumption that sustained high-intensity missile expenditure is a scenario the logistics system can support. That assumption was wrong, and the gap between the rate at which the Navy can fire missiles and the rate at which it can replace them, whether through at-sea reloading or industrial production, is the most significant capability deficit the surface warfare community faces going into the next conflict. The Navy fired 850 Tomahawks in 5 weeks. It produces 60 to 90 per year. The ships that expended their magazines spent 3 weeks each in port being reloaded one missile at a time. The tram system that could have kept those ships in the fight exists, tested, validated, and sitting in a developmental testing facility, waiting for the operational certification process to complete. The production lines that could replace the expended stockpile are running at a rate designed for peacetime deterrence, not wartime consumption. Every one of these gaps was known before Operation Epic Fury began. Every one of them will still exist when the next campaign starts. And that brings the campaign to the hardest question of all. The question that is hardest to answer in peacetime and most expensive to ignore in war. How long can the most powerful naval surface force in the world sustain combat operations before it runs out of the weapons that make it powerful? The destroyers will return to the fight. The magazines will be refilled eventually at a pier, one missile at a time over 3 weeks per ship. The stockpiles will be rebuilt slowly at 60 to 90 missiles per year over the years required to restore what 5 weeks consumed. The tram system will complete its certification process and join the fleet in time for a conflict that may already have been decided by the logistics gap it was designed to close. Modern warfare does not reward the most powerful weapon system. It rewards the system that can sustain its power across the full duration of the campaign. The question is never how many missiles a destroyer can fire. The real question is how many it can keep firing before the logistics system behind it begins to fail. If you found this analysis worth hearing, leave a comment, tap like, and subscribe in your own way for more.